for everyone. Okay, so I'm just going to go through all of the problems from the mock exam, and we can just go through each one, and then if you're able to type in the chat or annotate or unmute yourself if you like have any idea on how to, ideas for how to solve each of the problems, definitely please feel free to do that. But we'll just get started on this first problem here. So for the first problem of the this was the second problem, because the first problem was just like the checking the true false for the 1 + 1. So this is like the first real question. Was just asking to figure out the hypothetical reaction of how many moles of D would form in 20 seconds. So do you guys just want me to go over it, or do you guys want to like try to have a chance to figure out yourselves? What would you feel like is the best way for you to learn? Can you type in the chat or unmute yourself or whatever you want?
Can you go over?
Yeah, I can just like go through it. Okay. So for this reaction we have so it's 2A. Sorry. So it's 2A plus 4B yields C plus, my gosh, okay, plus 3D. And we have to figure out what the instantaneous rate of the reaction is at with the instant, or how many moles are going to form of the reaction. Sorry, my computer's messing up. Give me 1 second. How many moles of D are going to form in that 20 seconds? So, okay, so the first thing that we have to do is we have to figure out what the rate of the reaction is for D, because we're trying to figure out the number of moles of D. So if we figure out the rate of reaction, we can figure out moles over seconds. So the first thing that we want to do is we know the equation to figure out rate is that rate equals -1A over the change in concentration of A over delta T. And we also know, because we're trying to find D, we can also just equate the reaction equation for D as well, which is going to be positive, because D is a product, not a reactant, 1 over D delta D over T. So what we're given right now with this average rate is the rate of, oh, sorry, it's for B, not for A. We're given the average rate for B, which is this number right here, because it's just the rate of B. If you remember on the left hand, that rate is for like the entire reaction. So for the rate of B, in order to figure that out, we have to do, in order to figure out the rate of the entire reaction, we should plug in just the rate of B. So we have, because we have 4 moles of B, we're going to have 1 over 4, because the coefficient in front of 4 is, or in front of B is 4. And then we're going to have the rate of delta B over delta T is 0.0010 molar per second, because we're given that in the problem. So we have 0.0010 mole per second. And we also make this negative, because even though in the problem it's given to us as a positive number, it's decreasing. So that's why the actual rate of the entire reaction is going to be positive, because this is negative, because it's a reactant, so it's going to be decreasing over time. So you're going to basically divide this value by 4 in order to figure out the rate of the entire reaction. And this kind of makes sense, I think, if you think about it, because you're going for, in every 1 mole of reaction, you have 4 moles of B that are being used as a reactant for the problem. And so for the reaction. And so when you do 1/4 times 0.0010, you'll get 2.5 times 10 to the -4th molar per second. So that's the rate of the entire reaction. So in order to figure out what the actual rate of reaction for D is, we'll be looking for this value for the delta concentration of D over delta time. And so we can set 2.5 times 10 to the -4th molar per second equal to 1 over, and because the coefficient in front of D is 3, it'll be set to 1 over 3 times delta T, or delta D over T, which is the rate of D. And so in order to figure out this reaction of the rate of reaction of D being formed, we're just going to have to multiply the rate of the entire reaction by 3. So when we do that, when we do the concentration of D over T and we multiply this by 3, you're going to get 7.5 times 10 to the -4th molar per second. But the actual problem is asking you for the amount of moles that are going to form in 20 seconds. So in a 5-liter container. So you have molar per second right now, and you're trying to get moles. So the first thing you can do is that you have your time period, your 20 seconds. So you can multiply your 7.5 times 10 to the -4th molar per second. You can multiply that by 20 seconds in order to cancel out the seconds here and just have how many moles are going to be produced, or how much, like, how the concentration is going to increase over that 20-second period. So if you multiply 7.5 times 10 to the -4th by 20 seconds, you'll get 0.015 molar. At this point, we're really close to being done. We have 0.015 molar, but we're looking for moles, not the molarity here. So the molarity can be written out instead of just molar, it can be written out as moles over liters. And in order to cancel out that, sorry, I was going to move my chat that was on my screen. In order to cancel out the number of, or like that bottom, the liters, in order to just get moles, you have to multiply it by the volume of the container, which we're given as 5 liters. So once you do that, you're going to get 7.5 times 10 to the -2nd moles, which is, I think the answer was written as 0.075 moles of D. Do you guys have any questions about how I solved that, or how any part of it you want to go over again, or anything like that? Or is everything clear about that problem?
I have a question.
Yeah, of course.
So I guess I was just a little bit confused because it's like 2 parts where you have to find we have to use the concentration of B and D. Like how does that work?
So, okay, do you remember the equation? And I think the actual equation is like rate equals 1 over A delta A over delta T.
Yeah, yeah.
There's that whole thing, right? And so
Uh-huh.
that relates your rate of one reactant or product in the equation to all of the other like species in the equation. And
Hmm.
it gives you the rate of B, but you're really looking for D here. So if you use the rate of B, you can find the rate of the entire reaction, which is like the step that we took over here when you find that the rate of the entire reaction is 2.5 times 10 to the -4th meters per, or molar per second.
Yeah.
So you find that the entire reaction, you can plug it back into that bigger equation that was like rate equals positive 1D over delta, positive 1 over D delta concentration of D over delta time. And when you do that, you're able to find just the rate of D that's being produced. over like the time period that B has this average rate of 0.001 mole per second. And then from there, you can calculate the concentration by using the time and the volume. Does that make sense?
Yeah, except for like, so how do you know that the like for the concentration of B that's going to be like negative and not the like the like the concentration of D won't be negative? Like, how do you like flip that?
So the way that you have, and I'm just going to clear what I have written right here so I can write more. So if you remember like this equation, the rate rate equals 1 over A, negative 1 over A, times delta concentration of A, delta T equals negative 1. And this is for the reaction if it was like AA plus BB yields CC plus DD. And so if you had this reaction, then because your reactants are decreasing, this is written out, it makes it because the rate of the entire reaction is always going to be positive because like your entire reaction, because it's like going a forward, it's going to like a forward reaction, it has to be moving at a positive rate. Like you're not doing the reverse reaction, you're moving towards that faster reaction or like to the forward reaction. And because of that, the rate of your entire your entire problem has to be, your entire equation has to be positive, your entire reaction has to be positive in order to like balance it out. Because your entire reaction has to be positive, you have to have the reactants be negative because they're going to be decreasing in concentration. And so that's why like A and B have this like the negative parts of the equation in this, but C and D are always positive because they're products, so they're going to be being formed, so their rates are already going to be positive. So this negative sign kind of cancels out the negative of the rate here because they're reactants. So
Got it.
so when you have like this, you have delta C, and then if you were to continue and do it for delta T or for delta D, that's why, because it's just to balance out which reactants or products are being formed versus being like used up in the reaction. Does that make sense?
Yeah, it does make sense. Thank you.
Yeah, of course. Any other questions? Okay. If there aren't any other questions, then I'm going to clear and then we'll go to the next slide. So for this problem, it was just like a multiple choice kind of conceptual problem here. And it's asking in which case an ionic solid would dissolve in water and release heat. And so it's just asking us, and these different answer choices, they all use the word magnitude, and that just is like the absolute value. So it's not asking if there's like a positive, negative sign. It's just that like the actual value itself without a positive or negative sign attached to it. And so your different answer choices really revolve around the idea of a lattice energy, and the magnitude of how large the lattice energy is versus the magnitude of hydration energy or different interactions. And so I think the most important equation to remember for this problem is your delta H of your solution equals your delta H of your solute plus your delta H of your solvent plus your delta H mix. And if you remember that was in the beginning of chapter 13, so kind of like the beginning of this whole semester for you guys, probably when you went over talking about the talking about each of the different reactions for like when you mix solutions together and what energy is created versus when energy is like has to be used and you have an endothermic reaction. And so for this reaction, you have delta H solution equals delta H solute plus delta H solvent plus delta H mix. And so if you recall, your delta H solute is like the energy that's created or used up, your heat that's used up when you dissolve your solute into your solvent. So it's the bonds that are breaking in your like in your solute when you're dissolving it to make a solution. So that's the same thing as your lattice energy. The magnitudes of those delta H's are the same because your the lattice energy is like that energy within the bonds of your solute. So when you're dissolving it, the magnitude is the same as the delta H of your solute because it's the same energy that's being broken between those bonds. And then if you remember the delta H of your solvent and the delta H of your mix, when you mix the solutions together, you mix the solvent and the solute together, those two together, they create your delta H of hydration. So the delta H of your solvent is really similar to the delta H of your solute. It's just about, instead of the bonds between your solute particles, it's the bonds between your solvent particles. So for example, if your solvent was water here, the delta H of the solvent is like the bonds between the water that are being broken when you're mixing the solvent and the solute together. And your delta H mix, and so both your delta H of your solute and your delta H of your solvent are usually endothermic because they take energy because you need energy in order to break the bonds. But delta H mix is usually exothermic because it's always exothermic because it's the energy of the new bonds that are forming between your solvent and your solute. And so the way that you can determine whether or not a reaction is going to happen is if this delta H hydration, because it has that exothermic factor of the delta H mix, if that delta H mix is really negative and it brings the whole heat of hydration to be really negative and really large, and it's larger than the energy coming from your solute, if it's larger than that, if that's endothermic, it'll be a positive delta H sign. So if you have your delta H lattice energy that's smaller than your delta H of hydration, then you're going to get an overall delta H of solution that's negative because you'd be adding a small positive number to a really large negative number, and you'll get an overall negative delta H, which would make the entire reaction exothermic. If you remember, for your delta H's, a delta H that's positive is endothermic because it's absorbing energy, whereas a delta H, if it's exothermic, it's negative because it's releasing energy. And so the answer to this one would be the magnitude of your lattice energy is smaller than the magnitude of your hydration energy. So that would be the answer for the second problem. Does that make sense? Or if there's any part of that that's confusing, I can explain again. Is everyone good on that? We can go over it again if it's confusing at all. Okay, all good? No one move forward? Okay, let me clear. Okay, so now with the next problem is another like integrated rate law question, which a lot of these on this practice exam were. So this one is saying a first order reaction has a half-life of 120 seconds. And it says, what's the instantaneous rate of this reaction when the concentration is 0.5 molar? So because you're given that it's a first order reaction, you already are able to reference what equation you have to use for the problem. And so the equation that you have to use for a first order reaction is that T1/2 equals ln2 over K. And so you have this equation and you have your half-life already, and you already have your ln2 is just a number. So if you plug into this equation, you can figure out what your k value is, and then you can use that in order to figure out the instantaneous rate. Because the other reaction or the other equation that you really want to use in this for this problem is delta A. Oops. Delta A over delta T equals K times the concentration of A. And so if you're able to get your K here, then you already have your concentration of A, and then you would be able to get the instantaneous rate of the reaction. So when you plug into this one, you have 120 seconds equals ln2 over K. So in order to find your K, you just have to do K equals natural log of 2 divided by 120 seconds. When you do that, you get K equals 0.000578 1/seconds. And so now you have your K value to plug back into here. So you're looking to get delta A over delta T equals Ka. And now you have your K value. So you have 0.00578 1/seconds. And then you have your concentration of A, right? Because it's asking you specifically when your concentration of A is 0.50. And so if you plug that in, then you get your negative delta A over delta T as negative 2.9 times 10 to the negative third molar per second. And I think in the actual equation, they don't include the negative because they just included the positive as like the magnitude of the rate of reaction. So it was just 2.9 times 10 to the negative third molar per second. Are there any questions about that one?
Where'd you get the ln2?
So the natural log of 2, it's just one of like the equations. It's just like one of the equations like that you just have of
Oh, all right.
and the reason for that is like if you know the other integrated rate law equation that's like I'm trying to remember what it is. It's like one of the larger rate law equations. If you use that equation, you can you would do the natural log, you end up natural log because you know after 1/2 life you're going to have half of the original reactant, and so if you use that, it ends up canceling out into natural log of 2.
Got you. Okay, so it's always going to be that.
It's always that for first order reactions. Like if you're able to, I think the textbook has like a big table with all of the reactions or with all of like the equations in there for each of like the 0, first, second order reactions. All of them for the first order rate laws, it's always going to be natural log of 2 over K, which is equal to 0.693. If you ever.
All right, sounds good.
Anything else for this one? That was a really good question. Okay, if no other questions, then we'll go forward. And like if it's ever confusing, you just want to go over it all over again, that's not a problem at all. Just let me know or type it in the chat, or you can private message me. We can definitely do that. Okay, so now this one is kind of like it's like not really quite conceptual, but it's not really a calculation either. It's asking you if a certain reaction has a rate constant that has units in molar times 10 to the negative second, or like to the power of the negative second, and then seconds to the power of the negative first, what the overall order of the reaction is. So I think the easiest way to do this is to like basically write a rate law without using actual numbers in it. So if you had a rate law, you'd have rate equals K, and then it would be like the concentrations of all of your different reactants. And so if you like you were trying to find the actual order here. And so if you had, like even if you had 9 different reactants or whatever, the order of the overall reaction is always whatever all of the exponents add up to. So for example, if you had rate equals K A times B, because each of their exponents is 1, the order would be 2. But if you only had rate of A, it would be the order was 1. If you had rate equals K times A times B squared, then your overall order of your reaction would be 3 because you'd have 1 plus 2. So knowing that, it doesn't really matter. You don't need to know how many different reactants you have. You just need to know what the total number that they're all going to add up to is in order to find the order of the reaction. And so you can just kind of write it as 1 reactant to the X power because it doesn't really matter since you know the overall order is how all of them are going to add up. And so your rates are always measured in molarity over seconds. So you know that the order or that the label on your rate is going to be molarity over seconds. You're given that your rate constant K is going to be 1 over molarity squared and then seconds. And so if you have these negative exponents, that just means they go in the fraction, or they go like in the denominator of the fraction. And so what you're really trying to find out is how many powers your reactant is going to be raised to. But if you remember, like your reactants are always going to have a unit of molarity on them. So now you need to figure out what like the actual exponent is for your molarity here in order to cancel everything, or to make have everything in this equation make sense. So the one way you can do that is by multiplying this over here like this, doing molarity per second, and then flipping the equation over and doing the reciprocal. So doing molarity squared times seconds, which is just the opposite, the reciprocal of this, equals m to the x. So you would have molarity cubed now, and your seconds are going to cancel out. So if molarity cubed has to equal molarity to the x, then the only way to have it be equal is if x equals 3. Which means if your exponent is going to add up to 3, that means you have a third order reaction. And that the order equals 3. Do you guys have any questions about that one, or want to go over anything for that one again? Or is that all clear? Okay, if that one is all good, then I'll clear annotations. And then we can go to the next problem. Okay, so given the following rate law, how does the rate of the reaction double if both concentrations of X and Y are doubled? And so the rate law of this equation, I guess when I copy and pasted it in from Canvas, it just didn't copy. But the rate law for this one is rate equals K. Sorry, that's a really bad K. I let that get confusing with X's too. You have K, then you have X squared times Y. So the easiest way I think to think about it when they talk about like changing the concentrations of a rate law is to first find the rate if everything was set to 1. And so if you're trying to find out how the rate of the reaction changes, your K is going to stay the same no matter what. So by whatever factor that the reaction changes, like if the concentration is going to double, if it's going to be cut in half, whatever, your K isn't going to play any part in that, because for the same reaction, your K is always the same. So you can just set your K equal to 1. And then if you're going to have the reactions double, you can just arbitrarily choose a number. So I'm going to choose 1 because it's just easiest to do math with 1s and 2s. But you could do it with any number and then just do it again with double that concentration. So for example, here, we're just saying that the molarity of of X in this situation is 1, and the molarity of Y in this situation is 1. When we do that, we get our overall rate is 1 times 1 times 1 equals 1. Okay, so now we're saying, what if we have this exact same equation, we have this exact same reaction, except we're going to double our concentrations. So just like before, if we're going to divide our K's anyway, it doesn't matter what we set them equal to. So we'll just set it equal to 1 just to make things simple for us, because we set it equal to 1 in the first case scenario too. But now we have to double our concentration. So in our concentrations 1 in the first time we did the calculation, now let's make them 2, because we're trying to find a double. So we have 2 times 2 times 2. I just realized this is actually cubed. Sorry. So it would still be 1 over here because 1 times 1 times 1 is still 1. So this is all equal to 1 over here. But now you have 1 times 2 squared times 2 to the third. And when you do that, you're going to get 1 times 4 times 8. And you do that, you get 32. So your rate when you had them at like you had normal values was 1, but when you doubled values, it was 32. So if you were to divide these, obviously it's very easy when you have 32 over 1, it's just going to be 32. But if you were to do this with different numbers and say, I wanted to run this one time with calculations where I'm doing a concentration of 4 for each of them, and then again with a concentration of 8, it doesn't really matter. You can just divide the rates over, and no matter what, you're going to get the same, that the factor changes, or that the rates change by a factor of 32. Does that make sense? Is there anything that you want to go over, or is that unclear in any way?
Why did you divide by 1?
So we want to compare how the rates of the reaction changes once the concentrations are doubled. And so I was just doing, if this is our doubled concentrations versus our single, in order to figure out what the factor of it was, I was just doing the rate of this reaction, which I guess would really be 32 molar per second. I was just dividing this rate by the first rate just to see what the factor was. And since it's just 32 divided by 1, it's just going to be 32. Does that make sense?
Yes, thank you.
Okay.
I have one more question.
Yeah, of course.
So if it was tripled, would you just like, instead of 2, you'd put like 3 and then see what happens?
Yeah.
All right, thank you.
And it could even be like, what would happen if the concentration of X was doubled, but the concentration of Y was tripled? You would just plug in like 2 and 3, and it would you just have to do the calculation.
Oh, okay. Oh, sweet. Thank you.
Yeah. Okay, and then clear. Okay, so now this problem asks what the activation energy is for an equation, or for a reaction that triples its rate constant when temperature is increased from 20 degrees Celsius to 40 degrees Celsius. So for this one, I used one equation when I solved it, but I think there's an easier equation that we can use for this one. So the one equation that you could use to solve this one would be your equation that is the K equals A E to the negative EART. Give me 1 second. My mouse like always goes, it always like disappears on Zoom. So the one equation that you could use and you could manipulate to solve would be the equation that is K equals AE equals negative EART. And if you chose to use this equation, which is like I had used because I was just trying to think like fastest in the moment what I could do, you're gonna get like some like interesting like numbers because you have to take a lot of logs. So in the answer key that Odysseus gave, they use the equation natural log K. Let me just share my screen with you so you can see. they use this equation, they ran this equation, natural log K1 over K2 equals EAR over 1 over T2 minus 1 over T1. And so when you use this equation here, you would have your you would have natural log of 3 because your K tripled. And because you have your concentration of your K1 over your K2, if you do natural log 3, you just have to know then that your temperature is increasing from 20 to 40. So you have to just make sure that your T1s and T2s align with that. So you can just set the ln K1 over K2 equal to ln over ln of 3 because you know that you're going to be tripling your K values. So you don't have to actually know what the K values are. You can just use that ratio of K1 over K2. And then we're looking for activation energy here, which is EA over R. And if you remember, our R in this situation is 8.314. And then we have our 1 over T2 minus 1 over T1. And so the only thing that we have to do here is that in these equations, because our label on our R is in, which is our constant here, is in Kelvin, we have to convert our temperatures into Kelvin first. So if you remember how you convert from Celsius to Kelvin, is that you just have to do degrees Celsius plus 273 equals your degrees Kelvin. So for 20, you would do 20 plus 273. And for the 20, it's going to be 293 degrees Kelvin. And for your 40, because you'd be 40 plus 273, it's going to be 313 Kelvin. So those are your two temperatures. The only thing you have to keep in mind here is that when you did your K values, you did K1 over K2 equals 3. And so you have to make sure that your temperature is going to be increasing. So your K1 value has to be 40 and your K2 value has to be 20 to make sure that that makes sense when like your rate constant is tripling. So that's going to be K1 over K2 is 3, which means the larger value has to be K1, which means the larger temperature has to align with that. So it's going to be your 313 here. And then your other temperature is 293 Kelvin. And so in order to plug this in, you would just do natural log of 3, and then you would do ln of 3 equals EA divided by 8.314. Because that's just your constant. If you remember that from like the thermodynamics unit, that's just your constant. And so you have you have to divide your activation energy by 8.314, and then you have your two temperatures. So 1 divided by 313 minus 1 divided by 293 is negative 2.18 times 10 to the negative 4th. So your first step here would be to divide natural log of 3 by that value that you just got, and you're going to get equals 5,037. And equals activation energy over 8.314. and then you're going to multiply by 8.314, and you would get activation energy equals 41,900 joules. But all of your answer choices, or joules per mole, sorry, but all of your answer choices were given in kilojoule. So if you remember, in order to convert from kilojoules from joules to kilojoules, you would do 41,900 joules per mole times 1 kilojoule is 1,000 joules, or 10 to the third joules, and that equals 41.9. So 41.9 kilojoules per mole. Okay. Do you guys have any questions about this problem? Let me just open the chat, sorry. Okay, if you don't have any questions about that one, we're just going to clear the annotations and go back to the PowerPoint. Okay, so then the next problem was, which of the following statements best describes the conditions for successful formation of a product according to the collision model? And the different answer choices that you were given for this one were had a lot of the same similar thoughts here that revolved around the relative orientation of the particles and the amount of energy that the collision had. So for this statement, you could say, okay, so it's saying which best describes the condition. It says the relative orientation of the particles must allow for the formation of the product. This statement is true, but is it like the best statement here? We'd like read the other statements to figure it out. And so we know that like the relative orientation of the particles has to allow the formation of the product, because if you remember, like in the book, there are pictures of it, and I'm sure that Dr. Altina showed pictures of it too. You have to have things that collide in no meaningful way. So for example, if you have a collision where things aren't like hitting in the, like if you have a collision and it's two molecules and the one is red and the other is green, and the only way for them to be a successful collision is if the greens hit each other. Then if you had this reaction, it would be successful. But if you had a reaction where there was a red on the outside and the red on the other outside, but there was green on the one inside and green on this side, and they collided like this, it wouldn't be a successful collision because it wouldn't be the right way if you need to have the two greens colliding with each other. And similarly, if you had two reds colliding with each other, but not the greens weren't colliding with each other, then it wouldn't be a successful collision either. And so the orientation of the particles has to be correct in order to allow for the formation of the product. So that statement is true, but to figure out if it's the right, like if it's the best statement that we have here. So then we have the relative orientation of the particles has an effect only if the kinetic energy of the particles is below some minimum value. And this one isn't important for describing successful formation of a product, because the relative orientation of the particles has to allow for the formation of the product, as long as the particles have to be aligning in a way so that when they collide, they're able to form the product that you want to have, and not just colliding in a way that either forms something different or that doesn't form anything. So this one is not the statement that we want, because it is important, the relative orientation of the particles, according to the collision model. And then we have this statement that says the collision must involve a sufficient amount of energy to overcome the activation energy, and the relative orientation of the particles must allow for the formation of the product. So this part of the statement is like the same statement that we saw earlier. We just also have another component to consider here. So the collision must involve a sufficient amount of energy to overcome the activation energy. And if you remember what these graphs look like, you have like the reactants, the energy of the reactants, then they have to get over the activation energy hump, and then you have the reaction or the energy of the products here. So in order for a collision to actually be successful, you have to have the particles that can actually get over this, like this activation energy hump. If they don't have enough energy to get here, if they can only get, they collide and they collide in the right way, but they can only get up to here, then the reaction isn't going to proceed because they don't have enough energy. And so this statement is better than the first statement because it also considers the activation energy. So I'm going to get like a check plus because it's better than the first one, even though the first statement is true. And then it says, the last statement says, the relative orientation of the particles has little or no effect on the formation of the product. And we know that's not true because the orientation has to be correct in order for them to form the product. So for this one, the correct answer is this one right here. That the collision must involve a sufficient amount of energy to overcome the activation energy, and that it has to have the correct orientation. Do you have any questions about that at all? Okay, if there are any questions about that, we can go into the next one. So for this next one, we have a reaction and we know it's first order that's given to us in the equation here, or in the problem description here. And we also know that 80% of the reaction is going to occur in 30 minutes. And then it says, what is the half-life of this reaction? So for this one, we know that there's an equation for half-life. Sorry, my pencil just disappeared. That says that the initial concentration times 1/2 to the half-life over, or the time over the half-life is equal to the concentration at time t. So the way that you would write this out would be nt, which is the number of particles at a certain time, equals the initial concentration is n0. So n time is the concentration at a certain time, and initial is the initial concentration. And then the last part of the reaction is 1/2, which is because every time the reaction happens, it is like the amount of your material is halved each time. And so that's why it's the 1/2 to the exponent here. And so your t is the amount of time, and your t 1/2 is your half-life. So what we're trying to get here is your t 1/2. So you are not given actual amounts for your initial and your your reaction at 30 seconds or after 30 minutes, sorry. But you are given that 80% of your sample 80% of your sample reacts in 30 minutes. So we can just plug in 1 here for the initial reaction, right? Because you can just set it equal to whatever. So you could even think of it as, if we want to think about it in terms of percent, we could just say it's going to be set equal to 100. So if there were 100 grams total of H2O2, then 80 of them would have reacted because 80% of them reacted. So we have 1/2, and we have our time. We have 30 minutes. But then in order to figure out NT, so it says 80% of it has reacted. So 80% has reacted, and we're saying that we have 100 grams total. You're not going to have 80 here at time t. You're going to have 20 because 80 of that has already reacted. So all that's left is 20 grams. So the first step you can do is just divide by your 100 grams in order to just get 0.2 on this side. So you would do divided by 100 grams on this side and on this side. And you would cancel out this whole part of the equation, and then this would become 0.2 equals 1/2 raised to the 30 minutes divided by your half-life. And this is where the problem gets maybe a little bit tricky if you're not comfortable with logs, because we have the thing that we actually want is in the exponent, so we have to get that out of there. So in order to get something out of the exponent, we can take a log. So we take the log of both sides, we'd have the log of 0.2 equals 30 minutes divided by t1/2 times log 0.5, because, or log of 1/2, they're the same value. Because when you take the log, you're going to get the things out of the exponent are going to come in front, and then you can take the log of the base here. And so now you'd have, now this is a bit easier to solve. So now you have log 0.2 equals 30 minutes over t1/2, and remember your t1/2 is what you're trying to solve for, times log 0.5. And so you can just do log 0.2 divided by log 0.5 equals 30 minutes over your half-life. So once you do this, you're going to get, so you do log of 0.2 divided by log of 0.5. You're going to get 2.32. You're going to get 2.32. So you'd have 2.32 equals 30 minutes over your half-life. And so in order to get your half-life, you can just flip these two terms. And so then it would equal t1/2 equals 30 minutes divided by 2.32. And when you do 30 divided by 2.32, you'll get your value of your half-life to be 12.9 minutes. Does that make sense? Or are there any questions about how you solve for that or anything else? So much of this is just knowing, once you know the equation that you have to use, it makes solving the problem so much easier. Is everything clear for this one? Okay, I'm going to clear the annotations. Cool. And thank you guys when you say in the chat, just like saying that it makes sense and goes good everything. Thank you for saying that. Okay. Now this next problem is finding a rate law from experimental data. So it's asking us to find the initial rate data for a hypothetical reaction with two reactants, A and B. And so we're given three different reactions, and in the first two reactions, B stays constant, but A is changing. So in order to find out the order of A, we're going to use these two equations. And in order to figure out the equation of B, or the order of B, we're going to use the one in which the concentration of A is held constant, but the concentration of B is changing. So we'll use the latter two equations, or the latter two like trials. So in order to figure out the concentration, we can first do look at these two reactions and say, okay, so our first, we have a concentration of 0.312 molar in our first one, and our concentration of 0.104 molar. So in order to figure out, I'm sorry, that's a really weird zero. In order to figure out how much the concentration changed by, we can divide this we can do 0.03312 divided by 0.0104 in order to figure out by what factor they multiply by. So when you do this, you're going to get a factor of 3. So the concentration in trial 2 is 3 times that of the concentration of A in trial 1. And remember that the concentration of B is held constant. So B is not going to have, like B should not be changing the rate at all because its concentration is held constant. And so you have your initial rate in the second equation to be 2.03 times 10 to the negative 7th molarity per second. And then you have your concentration, or sorry, your rate of your first experiment to be 2.25 times 10 to the negative 8th molarity per second. And when you do that ratio, you'll get 2.03 divided by 5 e to the negative 8th. You're going to get just over 9. You're going to get 9.02. So remember, for experimental data, you can basically say that it's 9 here. And it's just a ratio, so we don't even need a label on that. But now you can look at them and say, okay, so the concentration increased by a factor of 3. And when that happens, the rate was increased to 9. So, or the rate like factor changed by a factor of 9. And so 3 to what power equals 9? So you could say like 3 to the what power equals 9. Well, 3 squared equals 9. So because of that, we know that the order of A is going to equal 2. So the order of A and we can do the same thing for our B. So I'm just gonna erase, actually I'll clear all drawings, and then we can do, so order A equals 2. And we can do the same thing for B now. And again, we want to use the reactions in which A is held constant, but B is changed. So we're going to use the bottom 2. And so for this one, you probably can tell pretty easily. But if we do 0.00400 divided by 0.00200, your concentration from trial 2 to trial 3 has been cut in half. So it's going to have, 4 is the larger one, and it's going to be a factor of 2 that the reactions are going to change. So then for this one, we have 2.03 times 10 to the negative 7th divided by 1.02 times 10 to the negative 7th. And this one might also have been easy for you to tell that it's going to increase by a factor of 2, but we can do the exact calculation in order to figure out. So it's a 1.99, which in these, with this trial data, you can just equate to 2. So when the concentration was doubled, the rate increased by a factor of 2. So when you do that, it's going to just be that the order of B is 1 because it only doesn't go by an exponential factor. It's just that when the concentration of B is doubled, the rate also doubles. So your order of B equals 1. And so your overall rate equation is going to be K, and then A will be squared. And then B is only going to be raised to the first power. So that will be, that's your equation for this experimental data. Any questions about any of that? Okay. there are any questions, and I'll clear the annotations and move forward. Okay, so now you have this equation. You have an equation where you have 2C4H6 is being converted to C8H12, and you're given the rate law for this, and you're also given your K value. So you can see here that your rate reaction is raised to the second power, which means your order is going to be 2. And so all of the integrated rate laws that you're going to use are going to be for a second order reaction. And so you're trying to find the time that's going to take in order for your concentration to decrease. So one of the integrated rate laws for a second order reaction is 1/A equals 1/A initial. So this A is at a certain time, and this A is at the starting time. And so it's 1/A equals 1/A initial plus KT. And so you're given your A initial right here, starting with this value. It's asking you to find how long it'll take to decrease to this concentration. So it's going to be this A, and you have your K value up here. So you can plug all these into this. Oops, I plugged in the wrong number. .007 equals 1/0.0100 molar plus K is 0.0852, 1/, molarity times seconds, and then you're going to multiply it by your time. And so in order to solve this one, you can do 1 divided by 0.007 is 142. We can just leave it as 142.9. And then you can simplify this as well and do 1 divided by 0.01, and that is going to be 100. And your units on that is going to be 1/molar. And then you'd still have your plus 0.0852, 1/molarity times seconds times T. And so you're trying to find this T value here. So you can just subtract your 100 from this side in order to get it to this side. So you would do 142.9 minus 100 equals 42.9, 1/molar equals 0.0852, 1/molar times seconds times time. And now in order to find time, you just divide over. So you would just divide by that 0.0852 value. So you would do you do 42.9 divided by 0.0852. And it would be T equals 503 seconds. Are there any questions about that? No? Okay, if that one made sense, we can go forward. Okay, so this question says a solution, a solution of two volatile molecular compounds, A and B, shows negative deviation from Raoult's law. And then it's asking you what that means in terms of the like the interactions in the molecules. So we'll look at the answer choices in 1 minute. I just want to show you these graphs first, because whenever I hear like deviation from Raoult's law, I always think of these 3 graphs from the textbook here, where it kind of shows you like a visual representation of what that looks like. And so if you're going to have a negative deviation, it's this one right here, where your actual vapor pressure is lower than what's expected. And that's because your your solute solvent interactions are so strong that because they're like so strong, it actually decreases the amount of evaporation, and like it decreases the vapor pressure because it doesn't want to turn into a gaseous state, because your solvent solute interactions are so strong that it's like holding them together as a liquid instead of having them form a vapor. So the answer to this one is the molecules of A interact more strongly with B than they do with an A with A and B with B. And what that really means is that your interactions between your solute and your solvent are so strong that they're much stronger than your interactions between your solvent and your solute, or your solute and your solute interactions. So let me show you just the answer choices so you can see the differences in each of the answer choices, just in case you didn't get this one correct. So this one is clear as air that are true. This one is this one. So the correct answer is going to be the molecules of A interact more strongly with B than with A with A and B with B. And so this one is the correct answer, but those other ones mean, so I'll click it as the correct answer, but this one means that the molecules of A interact strongly with other A molecules. If this one was true, there would be a positive interaction, because your A would be sticking with your solvent, or your solvent interactions, and your solute interactions will be stronger than your solute solvent interactions. And so if that happened, they would turn into a vapor at even a faster rate, because those interactions between your solute and your solvent would be so weak. Similarly, for the second answer choice, it would mean that if they interacted really weakly together, then you wouldn't have the negative deviation. You'd also have the positive deviation, because it's another way of saying that the molecules of the solute and the solute are stronger, or the molecules of the interactions of the molecules of A and A, or of the solute and solute, or your interactions of your solvent, or your B interactions are stronger than the interactions between A and B, or your solvent solute. And then finally, the last option is just kind of like out there. It says the 2 liquids have a positive heat of solution, which is kind of a different concept than what we're talking about right now with Raoult's law. Are there any questions about that one before we go forward? Okay, so then for this one, we have a certain reaction has an activation energy of 50 kilojoules per mole at 290 Kelvin. Approximately what fraction of the molecules has enough energy to make it go over the activation barrier upon collision? And so the equation, I think that is really easy to forget about here, is for the exponential factor. And this is from the Arrhenius equation, but the exponential factor actually discusses, or like it identifies specifically a number between 0 and 1. That is the likelihood that the collisions are going to, like how many collisions are going to be, have enough energy to get over the activation error, or the activation barrier, like hump in the graph. If you remember how the graphs look like reactants, and they have to go over the activation energy, and then they go down to products. So it's kind of like the exponential factor measures how many of them are actually going to be able to get over that bump and make an effective collision that can create a product. And so your exponential factor is like the Arrhenius equation. It's like the e to the number. And so it's actually e to the EA, which is your activation energy, over RT. And your R again is your 8.314, that constant that was used during the thermodynamics unit. So this exponential factor is measuring between 0 and 1 how likely it is that a molecule is going to be able to get over that hump. And so you're already given E is just like a number, and you're already given EA as 50 kilojoules per mole, and you're already given your temperature as 290, and R is just a constant, it's at 8.314. The only thing you have to do is that R is a constant and it is in joules. And so because it's 8.314, like I think it's like joules times K, and then like over moles or something like that. And so because it's in joules, you have to make sure that your activation energy is also in joules. And so because it's in kilojoules right now, if you have 50 kilojoules per mole, in order to convert into joules, you'd say 1 kilojoule is equal to 10 to the third joules. And then you'd have 50,000 joules as your activation energy. And so your exponential factor is going to equal E raised to the negative 50,000 divided by 8.314 times, sorry, I should put joules here, times 290 Kelvin. And activation is joules per mole, sorry. And so once you do this calculation, you would get 9.9 if you plug this into your calculator and you do e to the negative 50,000 divided by 8.314 times 290 Kelvin, you would get 9.9 times 10 to the negative 10th. And so your answer choices didn't include 9.9 times 10 to the 10th because negative 10th because of significant figures and because this value is so close to 1 times 10 to the negative 9th. I know it's a little hard sometimes with scientific notation, but if you think of it like it would be to the negative 10th, so it would be 1, 2, 3, 4, 5, 3, 4, 5, 6, 7, 8, 9, 9, 9. So in order to get it to go up to this 1, you would need like 1 times 10 to the negative 10th to push it forward. And so your answer is actually going to be 1 molecule in 10 to the negative 9th that would have the is the fraction of molecules that have enough energy to go over the activation barrier upon collision. So I'll just go back to your answer choices to show you again which one that is. So let me clear the annotations here. It would be this one right here, 1 times 10 to the negative 9th. That would be your correct choice. Okay. So the next one is in order to find activation energy, what numbers you have to plot. And so the correct answer to this one would be ln k versus 1 over t, where your slope is negative EA over R. And so for this one, let me show you. The Odysseus guide again, where the equation, your equation would be that you would have the Arrhenius equation is going to be natural log K right there. If you see it, natural log K equals negative EA over R times 1t plus ln A. So if you were to think of that as, if you were to think of this in like my equals mx plus b format, you could think of it as, I don't know why it's like writing so ugly, but it would be ln k here. So if you were to like think of this as y equals mx plus b format, your y, which is going to be your ln of k. So that's when it's saying ln of k, it's saying your ln of k is going to be your y versus 1 over t. So 1 over t is going to be your x here. And then your b in this equation would be your natural log of a, which is your y-intercept. And so negative ea over r is your m, which is your slope. Okay, does that make sense? Are there any questions about that one? Okay. If not, we'll move forward. Okay. So the next one is just asking which are miscible liquids. So if you remember, miscible liquids are the ones that can actually like combine together that have the similar forces. So if you remember, like dissolves like, and that that means that like polar substances are going to divide or like going to dissolve into polar substances, and that non-polar substances are going to dissolve in polar substance, or sorry, non-polar is going to dissolve into non-polar, and polar is going to dissolve into polar. And so because of that, we can go through each of these to decide which are going to be miscible liquids that will actually mix together and have similar forces and are like polar or non-polar. So for this first one, hexane is C6H14, which is very non-polar. But water, as if you remember, is non-polar. So hexane and water are not going to be miscible liquids. However, we have acetic acid, which has CH3COOH. And so we see this OH, we see that means hydrogen bonding, and we have water that's hydrogen bonding. So they're both very polar, they both have the same intermolecular forces, they both have that hydrogen bonding. And so they're going to be able to mix together and like dissolves like. So because of that, they are going to be miscible liquids. Then for this last one here, I think is the trickiest one. You have hexane and carbon tetrachloride. And so hexane, as we might have just discussed in the first one here, is very nonpolar. It's just carbons, which is like a chain of carbons that's completely covered by hydrogens. It's all the way canceled. All the dipoles cancel out. It's a very nonpolar. Carbon tetrachloride, you might think like, oh, chlorine, is really electronegative. But when you have 4 chlorines, all of those dipoles cancel out, which actually makes CCl4 nonpolar. And because of that, that's also a miscible liquid. And so the answer to this one was that both Y and Z are miscible liquids. Are there any questions about that one? If not, then we'll just keep it moving. Okay. And if you have questions about anything, always feel free to like interrupt too or type in the chat. Okay, so this problem is another like conceptual one that is asking about your rate constant. So if the one we had previously gave you your rate constant and asked for the order of the reaction, but now they're giving you the order of the reaction, they're asking you for the units of your rate constant. So your rate law is rate equals K A squared B C. And so we know that our rate is always measured in molarity per second. We're trying to find the units on our K. Our A is going to be measured in molarity, right? That's squared. Our B is going to be measured in molarity. That's only raised to the first power. And our C is also going to be measured in molarity, and it's also raised to the first power. So what we really have here is like molarity times molarity times molarity times molarity is going to give us a molarity to the 4th factor here. So kind of like how we had done the before, we like kind of did like we like flipped the equation in order to figure out what the units were on or what the order would have been on our molarity here. Now we're kind of doing the opposite. We're going to divide by molarity here in order to figure out what the units are on our K constant, because that's what we don't know. And so we would do K equals molarity per second times 1 over molarity to the 4th. And so one of our molarities is going to cancel out, right? But we're still going to have 3 remaining. And so that would mean the units on our K are going to be 1 over seconds times molarity to the 3. But because it's all in exponents and not in a fraction, because if something's in the denominator, you used to give the negative fraction. It's going to be K, and the unit on K is going to equal K equals second raised to the negative 1st and molarity raised to the negative 3rd. Do you have any questions about that one? Or anything else you want to go over about that? Okay, seems like you guys are good on that. Okay, so now we have a second order reaction has a rate constant of 1.4 times 10 to the negative second, 1 over molar times second. And then it's asking after 60 seconds, what's the concentration of B going to be if the initial concentration of A was 0.025. And I think this might have been one of the hardest problems on the whole mock exam. So they give you a little hint for this one that says solve for concentration of A and then use stoichiometry. So right now we're not even going to consider B. We're just going to think about A. So we're given that it's a second order reaction. So we can use our integrated rate laws again. And so if it's a second order reaction, that's going to give us the equation 1 over A equals 1 over A initial plus K times T. So that is 1 over A. And again, 1 over A means 1 over A at a certain time. Equals A initial plus KT. And so now what we're solving for here is going to be the concentration of A after 60 seconds. So what we can do is plug in everything except for that. So we have 1 over A equals 1 over A initial, and 1 over A, or sorry, A initial equals 0.25. So 1 over 0.250 molar plus K is 1.40 times 10 to the negative second molar to the negative 1st, and then seconds raised to the negative 1st. And then our time, because we're trying to find concentration of B after 60 seconds, we're first going to find the concentration of A after 60 seconds and then use stoichiometry from the equation. So our time is going to be 60 seconds. So if you do all of that, your 1 over A value is going to be 4.84. If you like do the calculation on this, because this equals 4, and then if you multiply these two together, they equal 0.84. So when you add, or when you multiply and add these, then you're going to get 4.84 over 1 over molarity. But we actually want the concentration of A, and we have it as 1 over A right now. So we just have to do 1 divided by 4.84 equals A. And so A equals 0.207 molar. And so I think this was the most confusing part of it, is that you have your concentration of A after 60 seconds. But what you really need to know is your change in A, because you're trying to solve for your change in B if your initial concentration of B is 0. And because A is a reactant, it's going to decrease over time. So our initial concentration was 0.250. Oh, sorry, I add an extra 0 in there. .250 molarity minus the number we just got. Sorry, that was supposed to be an M. 0.0207. Why do I keep adding extra 0? 0.25 minus 0.207 molarity, and that is going to equal 0.043. And so that's our molarity for A. But we have to consider that every time the reaction runs, right, for every 1 mole of reaction, 1 mole of A is created, but 3 moles of B are created. So in order to actually get how much B is created, you have to do stoichiometry. So you have 0.043 moles A for every 1 mole reaction, but for every 1 mole A in the reaction, there's going to be 3 moles of B. And so when you do this, I guess I shouldn't really say, I want to correct myself. I had said for 1 mole of reaction. It's not really for 1 mole of reaction. It's just for like this specific reaction over this time period. So for every 0.043 moles or molarity of A for this reaction, there's going to be 1 mole of A created for every 3 moles of B. And so you're going to have to multiply this together and you would get 0.130 molar B in every time this reaction happens in 60 seconds. So your answer for this one is 0.130 molar of B. Are there any questions about that one at all? I think that was a pretty confusing one. So definitely don't hesitate to ask questions.
Wait, how come it's 1 over A? Like that part's confusing.
Just like how before, like how I had said, there's like the table of like all those different reactions for each of the integrated rate laws. This is just because we're told it's a second order rate reaction, or sorry, a second order reaction. There is a second order rate law that's the integrated rate law, and that's 1 over A equals 1 over A initial plus K over T. It's like the way they solve for that is like an integral and stuff like that. So we just don't go over it in class, but it's just, that's just the equation that you're given for a second order rate law.
Okay, got it. I tried to do it with something else. I think that's why I messed up. But okay, thank you.
No, you're good. Any other questions? Okay. I feel like so many of these, if you do the wrong equation or like you don't know the right equation, like it's so easy to get the wrong answer because there's just so many different equations. So I think it's like to have a table, since the exam is open book, to have the equation for, or like the table from your textbook with all the different equations is probably really important to have. So for this one, it asks what is true, what is not true about 0 order reactions. So I want to show you all the different answer choices so we can go through them. So it says, so which of the following is not true? The half-life of the reaction is A initial divided by 2K. If you were to like look back at your sheet with your equations for half-lives for 0 order reactions, this one is correct because it's not, it's just completely dependent upon the initial reaction divided by the rate constant. So this one is true, so it's not going to be the correct answer. Then the rate reaction remains constant throughout the reaction. And so the rate of reaction does remain constant. If you remember, the whole thing about zero order reactions is that the initial or like the concentration just literally doesn't matter because it has no impact. The rate laws are just rate equals K is rate equals K, and then your A is A to the 0 power. And if you remember, A to the 0 literally goes down to 1, so it's literally just rate equals K. Rate equals K. So your concentration has no effect. So no matter what the concentration is, your rate of your reaction is going to stay exactly the same. So that is true, so it's not going to be a correct answer here. Then this one, the units of K are meters times second to the negative first power. This is true because if you remember, your rate is measured in molarity per second. If your rate of your reaction equals your K value, then your K value has to also be in molarity per second. And so because of that one, this is also true. And so that is going to be, the correct answer is going to be this one. And does a plot of concentration versus time is curved, not linear? That's not true because just like I talked about earlier, how the rate of reaction literally does not depend on the concentration. If you had concentration versus time, because no matter how your concentration changes, it's just about how much time has passed. Your rate of reaction is going to remain exactly the same. It's just a linear graph. So like at any point in your reaction, your slope is always going to be the exact same because your rate of reaction is always the same. So for this one, the plot is actually linear for a zero order reaction. So the correct answer, which is false, is that a plot of concentration versus time is the curve, not linear. Are there any questions about that one? Okay. If not, we'll keep going. And so this one asks what the instantaneous rate of a reaction is. And so we can go through each answer. So the correct answer is B, the slope of the tangent to the curve of concentration versus time is the instantaneous rate. But we can go through each of the other answers and then go back to this one. So the average rate divided by the time the reaction took. So the average rate is your average rate, not your instantaneous rate. Your instantaneous rate is your rate at that exact moment. Your average rate is like your rate over a certain amount of time. And so the D is not the correct answer. That would be referring to the average rate, not to the instantaneous rate. And then B is saying how long it takes to get to the transition state of the reaction. And so that one's definitely not this one because our instantaneous rate is at one moment, at one point. That's not what this is. And then the other one is also referring to average rate, the change in concentration divided by the time passed. That's the definition of an average rate, right? It's has a certain amount of time passing. It's how the concentration is changing over that time. So this is your average rate, not your instantaneous rate. So just in case you're not familiar with the idea of like having the curve or like the tangent line, if you have a curve, right, and you have your concentration of your reaction over time, and so if you have a reaction that's decreasing over time, right, and it's a curved line. Let's say this is 10 seconds here. If you wanted the slope at this exact point, it's just this one single point, so that you would get the rate at that point would be to have a line that only touched the curved line at just that one point. So I didn't really do a great job drawing that on my line here. But if you have a line that looks like this, then you'd want just that one point. And so you'd have a line that just touched the line at that one single point. And the slope of that line would be equal to the instantaneous rate, the rate at just that single moment. Are there any questions about that? Okay. So this next question is about Henry's law. So it says the constant for oxygen is 2.4 times 10 to the 3 molars per ATM at 0 degrees Celsius. And then it also gives you the constant at 25 degrees Celsius. So it's 1.3 times 10 to the negative third molar per ATM at 25 degrees Celsius. And then it's saying that O2 gas under 5 ATMs of atmospheres of pressure at 0 degrees Celsius, sorry guys, is how many times more soluble than O2 gas under 2 ATM of pressure at 25 degrees Celsius. So the way to get started with this one is to know the right equation to use. So to find the solubility using Henry's law. So for this one, you have so the solubility of Henry's, or the equation for solubility would be S equals S gas equals KH times, oh my goodness, my computer is moving up. SH times K, or sorry, S of the gas, which is the solubility of the gas, times K, which is the constant. And so KH is Henry's constant, which is the values that you're given at the different temperatures, times the pressure of the gas. So let's start at 0 degrees Celsius. So if we find the solubility at 0 degrees Celsius first, that'll be S equals, we've given our K already, 2.4 times 10 to the negative 3 molar. And we are given, sorry, it's molarity over ATM. And we're given our pressure as 5 ATM. So when you do, you'll do that equation, you can solve for this one. So if you do 2.4 E negative 3 times 5, you get 0.012. 12 molarity. And then you would do it at 25 degrees Celsius. And it's the same equation again, but you're given a different constant. So your constant is 1.3 times 10 to the negative third molarity per ATM times, and this one is given a different pressure too. It has 2, it's 2 ATM. So times 2 ATM. And if you do that, you're going to get 1.3 E times 10 to the negative 3 times 2 is 0.00206. Oh, sorry, 0.0026 molar. And so it's asking you how many times more soluble it is. So in order to figure out how many times more soluble it is, you just have to divide the solubility of the first one by at 0 degrees Celsius by the solubility of the second one at 25 degrees Celsius. So you would do 0.0012 molar divided by 0.0026 molar, and that is 4.6. And so your answer for this one is that it's 4.6 times more soluble. Is everything clear with that one? Okay. We'll go to the next problem then. So we're given a second order reaction has a rate constant that is equal to 3.1, or sorry, 3 times 10 to the 9th, 1 over molarity times seconds, and it's at 25 degrees Celsius is our temperature. And we're also given our initial concentration of our reactant here. So we can just call that MnCl. CO5 is 1.0 times 10 to the negative fifth molar. And then it's asking how long it's going to take for 90% of the reactant to disappear. Okay. So we're trying to solve for T, but we kind of have like two unknowns for this one because the equation we know we have to use, we've used it a few times before now, is the second order integrated rate law, which is 1 over A equals 1 over A initial plus KT. And so we're given the initial concentration, right? And we're given our K value, but we're trying to solve for T, but we're not outright given our A value here. But we are saying how long it's going to take for 90% of the reactant to disappear. So if we're given our initial concentration and we're saying how long it's going to take for 90% of that to disappear, we can say, okay, in order to figure out the concentration of A at a certain time, we're going to just take 1 times 10 to the negative fifth molar, which is our initial concentration, and we can multiply it by 0.1. And the reason we can do that in order to figure out the concentration at a certain time is because we're saying 90% of the reactant has disappeared. So if 90% of the reactant has disappeared, then only 10% is going to be remaining. So 10% is 0.1. And so because of that, we're going to say that after 90% of the reactant has disappeared, when we're searching for this time, that only 0.1 of it remains. So you'd have 1 e to the negative fifth times 0.1, and you would get a value of, 1 e negative fifth times 0.1, you would get 1 times 10 to the negative 6. I don't know, I didn't just do that in my head. So 1 times 10 to the negative 6 is your value for your A at a certain time. And so now you have everything that you need in order to plug into your equation. So let me rearrange it so that we can actually put things into our equation. So again, it's 1 times 10 to the negative sixth here, molarity. And so now we can put it into the equation here. So we have this value for A because we know only 10% of it's going to be remaining. So the value at A at the time is going to be 1 times 10 to the negative sixth equals 1 over, and we'd have our initial concentration, and we're given our initial concentration as a 1.0. I can add a 0.0 in here for sig figs. 1.0 times 10 to the negative fifth molar. And we have plus KT, and we're given our K as 3.0 times 10 to the ninth, 1 over molarity times seconds. And T is the only missing variable now, which is also what we're searching for, so that's good. So now we can do, what we can do is we can take 1 over 1 times 10 to the negative fifth. We can subtract that over to the other side. So we can say 1 times 10 to the negative 6 molar minus 1 over 1 times 10 to the negative fifth molar equals 3.0 times 10 to the ninth, 1 over molar per second, T. And so if we go up here, 1 over 10 to the negative 6 minus this value, these are both just numbers. So you can plug this into your calculator and you can do 1 divided by 1 divided by 1 times 10 to the negative 6th. And you can subtract 1 divided by 1 times 10 to the negative fifth. And when you do that, you would get a value of 900,000. 900,000 1 over molar equals 3.0 times 10 to the ninth 1 over molarity seconds T. And then you have to divide over this K value in order to solve for T. So once you divide by 3 times 10 to the 9th, you would get 3 times 10 to the negative 4th seconds. And it would actually be 3.0 times 10 to the negative 4th. First day phase. Are there any questions about how to solve that one or anything? Okay, if you're all good on that one, then we can go forward. And now we're kind of back at colligative. I know we've done a lot of integrated rate laws, but now we're going to do a colligative properties question. And so if you remember for freezing point depression, you'd have delta T F, which is the change in your freezing point, equals your KF times your molality. So what we're given here is that we're given 2 grams of an unknown electrolyte is dissolved in 50 grams of benzene. And we're given a new freezing point. We're also given the initial freezing point, and we're given our KF value. But we're not just searching for anything within this freezing point equation. We're actually trying to find the molar mass. But we can kind of work backwards from what we get from the from this equation in order to figure out the molar mass, because we have the moles or we have the grams of the unknown electrolyte, because what we're really searching for is the moles of this unknown electrolyte that was dissolved in the solution. We can then figure out the molar mass of that. So hopefully this might not make sense to you right with that explanation, but hopefully as we do the problem, it'll make more sense. So this delta TF is the change in freezing point. We're given that the freezing point of pure benzene is 5.48 degrees Celsius, but the freezing point of the new solution is 3.77 degrees Celsius. So the first step is to figure out what delta TF is. So if you have 5.48, in order to figure out the difference, you can do 5.48 degrees Celsius minus 3.77 degrees Celsius. And that equals a 1.71 degrees Celsius. And we can plug that back into this equation in order to figure out the molality, because we're given KF. And if we have the molality and we have the volume and we have the volume, the number of liters of the, or sorry, not the volume of liters, if we have the molality and we have the grams of the solvent, we can figure out the number of moles of the solute. So when we have the equation delta TF equals KF times M. So we have our TF now, 1.71 degrees Celsius equals KF is 5.12 degrees Celsius per molality. And then we need to just find the molality. So if we do this, we can just divide 1.71 divided by 5.12, and we get 0.334. So our molality equals 0.334 mole. And so now we have our molality, right? But we're trying to find the number, or we're trying to find the molar mass of the unknown compound. And so what we really need to do is find the number of moles. So before we can, so first what we should say is that the molality expression is molality equals moles of the solute over kilograms of our solvent. And we have our molality already, we were given our grams of our benzene, which is our solvent. So in order to solve for our kilograms of our solvent, we have to do 50 grams of benzene and convert it into kilograms. So for every 1 kilogram of benzene, there is going to be 10 to the 3rd grams of benzene. And so you're going to do 50 divided by 10 to the 3 is going to be 0.0500 kilograms benzene. And so we would do molality is 0.334. Mole equals the number of moles of our solute, which we want because our solute is our unknown electrolyte. And so if we divide by our the mass of our solvent, then we can get we can get the moles of our solute. So we would multiply over this 0.005. So then the number of moles of our solute are going to be 0.0167 moles of our solute. So we're so close to being done now. We're trying to figure out the molar mass of our unknown electrolyte, and we have our number of moles of our unknown electrolyte. But in order to figure out our molar mass, we can just do, because molar mass is equal to grams over mole, we can do the mass of our unknown electrolyte divided by the number of moles of our unknown electrolyte. So we do 2.00 grams of our unknown divided by 0.0167 moles. And we get our mass to be 120 grams of our divided by, 120 grams per mole of our unknown electrolyte is the molar mass. You guys have any questions about that one? Okay, if not, that one's good. Then we'll move forward. And we'll have 2 more problems to do. Oops. So it says the reaction that occurs in a breathalyzer. It gives us the rate of that reaction. It's asking us what the rate of disappearance is at that moment. If the rate of the reaction or if the rate of the appearance of a different substance is 1.24 molarity per minute at the time. So for this one, we have our rate of our one reaction. So we have to figure out what our other reactions are using, what the rate of our other reaction is using the stoichiometric coefficients. And so if you remember from the first problem that we did, rate equals -1 over A delta T. And so equals the rate of appearance of a product, 1 over that product, the positive rate of positive 1 over C delta C. And I should do delta concentration of A over delta T. And so we can use this reaction again and figure out our overall rate and then plug that back in, just like how we did for the first one here. So if we know that our rate of appearance is going to be of the one of the products here, it's going to be this product, and the rate and our coefficient, our stoichiometric coefficient is 2 here. Then we can figure out the rate of the entire reaction for 1 mole of the reaction. So for 1 mole of the reaction, there's going to be 2 moles of C, and we know that our rate of our appearance here is 1.24 molarity per minute. And if you multiply these together, then the rate of our overall reaction is going to be 0.62 molarity per minute. Okay, so now we have our overall rate, but we need to find our rate of disappearance of another substance. And that substance is C2H6O, which is this right here. And so again, we have our rate equals -1 over A because it's a reactant, and our stoichiometric coefficient is 3 for this one. So -1 over 3 times the rate of delta C2H60 over delta T. Now, our rate that we can plug in here is the rate that we just solved for using the other equation, using our appearance of CR2 SO4 3. And so we have our overall rate of our reaction to be 0.62 molarity per minute. So in order to figure out what the rate of reaction is of the C2H60, we just multiply over we multiply over 3, which is, we'd just be flipping the fraction over here. And so you would do 3 times 0.62, and you would get, for the delta C2H60 over delta T, you would get 1.86 molar per min. That's an 8. Are there any questions? And oh, sorry. So your actual rate is going to be negative here, right? But because it's asking for your rate of disappearance, it's like how Dr. Muniz talked about rate convention. It's going to be positive because it's your rate of disappearance. So it's like how you talked about like withdrawing from the bank. You wouldn't say like, oh, I'm withdrawing negative $500. You would just say I'm withdrawing $500. Your rate of disappearance is just positive. It's a 1.86 molarity per minute. Was your answer? Any questions about that one?
Does that be per second or does that not?
No, it doesn't have to be per second. If your answer choices were in per second, you could just convert from minutes to seconds, but all of your answer choices were in minutes. Okay. Clear, and then we just have one more question. So we have there's a 10-degree increase in temperature from 25 degrees Celsius to 35 degrees Celsius. And the reaction, it doubles the rate of a slow reaction. So what's the explanation of this? So these were the answer choices that you were given. The first thing that you can do is immediately eliminate A and B. Because if you remember, if nothing else is changing, your activation energy can't, like, it doesn't change. So like just because your temperature increased, your activation energy isn't changing because it's the exact same reaction. The only time that like an activation energy might decrease is if you have a catalyst or something in there, not just because of temperature. That doesn't actually change the activation energy. And so you can immediately eliminate A and B from your options here, the first two options, because the activation energy, no matter what happens to it, it's not going to have any impact on your, like with the activation energy, the changing of temperature is not going to have any impact on activation energy. So then you're left with two options. It's that the collision frequency doubles or the number of collisions having the required activation energy doubles. So the answer is the last option, answer E, the number of collisions having the required activation energy doubles. And the reason is because even though the collision frequency might double, you would need the actual collisions that would have like the amount of activation energy to get over that hump in order to actually have the reaction proceed that would give you, that would actually be able to double the rate of the reaction. And so because of that, it's not just the collision frequency that matters, it's the number of collisions that also have the required activation energy that doubles. And because of that, your rate of a slow reaction could double. So that is the entire practice exam, and it's 4 o'clock. So if you don't have any other questions, you're totally good to go. If you have any questions, feel free to stick around and we can definitely talk through anything else that you need.
All right, thank you. Have a good day.
You too.
Bye.
Thank you so much. Really helped.
Good, I'm glad.
Thank you. Have a good day.
Of course, you too. Do you have any other questions? Okay, if you don't have any other questions, I'm going to end the meeting, okay?